Welcome back. So we've been talking a lot about how to solve systems of differential equations, matrix systems of first-order differential equations, x dot equals ax, where a is a matrix and x is a vector of states. And I essentially, if x is an n-dimensional vector with n components, a is an n by n matrix, and this would represent n first-order ordinary differential equations, a first-order differential equation for x1, for x2, for x3, and so on and so forth, down to xn. And we've looked at simple cases where A has distinct eigenvalues that are not repeated. And so today I'm going to talk about what happens when you have repeated eigenvalues. So specifically, I'm actually going to look at two cases, two different A matrices that have repeated eigenvalues. The first one I'm going to look at is the case A equals 1, 0, 0, 1, which is almost trivially easy because it's already diagonal. But again, this does have two repeated eigenvalues, lambda equals 1 and lambda equals 1. So this is going to be one case we're going to look at. And the other case we're going to look at is this similar case, A equals 1, 1, 0, 1. So this also has the same repeated eigenvalues, lambda equals 1 and lambda equals 1. But we're going to show that these have very, very different dynamics. These have very different dynamics and different solutions for these two cases, even though they both have repeated eigenvalues, lambda equals 1 twice. Okay, and in the other cases I've shown you in the past, there is essentially this idea that you can diagonalize A with eigenvalues and eigenvectors, diagonalize A with eigenvectors and eigenvectors and eigenvalues. Eigenvectors and eigenvalues. And specifically, my eigenvectors come in a matrix T, and my eigenvalues come in a diagonal matrix D. And if I have these eigenvectors and eigenvalues, then I can take T inverse A T, and that's going to equal this diagonal matrix. And what we've been assuming up until now is that this diagonal matrix essentially consists of lambda 1, maybe I'll write lambda 2, lambda n, and zeros everywhere else. I've been kind of implicitly assuming that all of these lambdas are distinct and different eigenvalues, not like this case where I have repeated eigenvalues, where I have two eigenvalues that are lambda equals 1. I've been kind of implicitly assuming that I have distinct eigenvalues here. And so this is a little bit of a special case I'll tell you about, and then we'll revisit this kind of general diagonalization here. And so specifically, there are some kind of math theorems. I don't usually give you like theorems and proofs and like real kind of rigorous math. I give you just the feeling of the math. But there's some important properties of when you can diagonalize a system like this, when the eigenvectors T form a complete basis for this n-dimensional vector space that my vector x lives in. So, x lives in an n-dimensional vector space. This means it's an n-tuple of real numbers. It's a vector, okay? And this matrix T of eigenvectors, all of those eigenvectors, all of those directions will span a basis for this n-dimensional vector space if all eigenvalues, if all the eigenvalues lambda of A are real and distinct, meaning they're not equal to each other, then essentially my eigenvectors T, the eigenvectors T, span this n-dimensional vector space. They span Rn. And what that means is, this is a real n-dimensional vector space. What that means is that any vector you could name, any x in this space that you could possibly name, is going to be a linear combination of the columns of T, or of the eigenvectors of my A matrix. And that's a really useful property. That means that kind of any initial condition I have, any initial state, any x vector in this space can be written as a linear combination of columns of my eigenvectors, the columns of the matrix T, which are eigenvectors of A. So they form a complete basis that spans Rn if the eigenvalues of lambda are real and distinct. So I'll underscore real and distinct. If they are not real or they are not distinct, then there might be some issues with this diagonalization procedure. I won't be able to write it as a purely diagonal system. There might be a couple of off-diagonal entries like this guy here. It's impossible to perfectly diagonalize this matrix. I'm always going to have this off-diagonal entry here in my D matrix, no matter what I do. There's no coordinate transformation that will get rid of this little upper one that's not diagonal. And so there's exceptions to this idea that you can diagonalize your matrix. In particular, if I have repeated eigenvalues, sometimes I won't be able to get perfectly diagonal matrices, but you get things that are close to diagonal. And I'll show you that kind of in this lecture. Good, so we'll revisit this in a little bit, but I kind of want to zoom into these two matrices and look at what is different just by changing this little number here. Okay. So clearly, lambda 1 equals 1 and lambda 2 equals 1 are both eigenvalues. So this is what we call a repeated eigenvalue, e-value. For any diagonal matrix or any matrix that has a lower triangle of zeros or an upper triangle of zeros, you can verify, I'll just write this down. If I have a big A matrix and I've got, A1, A2, AN, and I've got some stuff up here, A1, 2, A1, 3, A2, 3, So these are non-zero. But I have zeros below the diagonal, then the eigenvalues of this matrix are the diagonal entries. These are, lambda 1 equals A1, lambda 2 equals A2, and so on and so forth. And this is really easy to see. You literally take this matrix minus lambda times the identity, lambda, lambda, and then you take its determinant and set it equal to 0. And because of the structure of this matrix, the determinant is going to be the product just of the diagonal entries because it has this lower triangle of zeros. And so the product of that determinant is just going to be A1 minus lambda times A2 minus lambda times A3 minus lambda times ... And so the lambdas that satisfy that characteristic equation, that determinant equals 0, are exactly lambda equals A1, lambda equals A2, and so on and so forth. So when I say I can just read off these eigenvalues, or the eigenvalues are 1 and 1, I'm using this property here. So you could kind of pause this video if you want and really convince yourself that for this kind of matrix, the eigenvalues are going to be on the diagonal. Same thing if I transpose this, so I have numbers on the bottom and zeros on the upper triangle, same exact thing applies. Okay, I'm going to erase this, and then we're going to revisit this. And so the next thing I'm going to do is compute the eigenvectors. But the eigenvectors of this matrix are kind of trivial because we know that one of the eigenvectors, C1, is going to equal the 1, 0 direction, and another eigenvector, C2, is going to equal the 0, 1 direction, because to some extent this thing is already diagonalized. So the normal kind of x and y coordinates, x and y unit vectors, are already going to diagonalize the system because it's already diagonal. I don't have to do any change of coordinates. So my T matrix, if you like, is going to be the identity because it's already diagonal. My system's already diagonal, so I only multiply it by the identity to diagonalize it. Good. And the way you think about this, you could solve for these if you liked. You could literally solve for these by taking A minus lambda identity, A minus lambda to the identity, and then trying to find what x vectors would map to 0 for that lambda equals 1. And this is kind of trivial because A minus lambda times the identity is a matrix 0, 0, 0, 0. So literally any x is going to map to 0 for that lambda equals 1 repeated eigenvalue. And so what we say is that this matrix has rank 0. It has 0 span in Rn. It has 0 rank. There are no vectors in this matrix. It's just a 0 matrix. And so it has a two-dimensional null space, basically, because this thing, any vector will map to 0. That means this has a two-dimensional null space spanned by this vector and this vector, the two eigenvectors of my system. Okay, so this was kind of a trivial case. We didn't have to go through all of this math because you can just read off that the eigenvalues are 1 and that it's already diagonal, so my eigenvector matrix is the identity. But let's look at this, this case here, this kind of more interesting case where I have this weird little upper one here, and maybe I'll do this in green. So similarly, I can write down that lambda 1 equals 1 and lambda 2 equals 1 are my repeated eigenvalues, because I can read it off because it's a diagonal matrix with lower triangle of 0. And now I'm going to look at the same A minus lambda I matrix, so A minus lambda I, and I'm still going to look for x that map to 0. A minus lambda I is this thing minus the identity is going to equal 0, 1, 0, 0. This thing does not have rank 0. It has rank 1. There's one vector that has a direction, and so this spans a direction. And so what we're going to find, essentially, because this is rank 1, it only has one eigenvector, or one x that maps to 0. And so we can find out what that is. We can literally take 0, 1, 0, 0, and we can multiply this by, you know, x1 and x2, and that's, we're hoping, going to equal 0. So let's just do that. That equals, you know, x2, 0, and we want this to equal 0. That's what we're looking for, are vectors x that map to 0. And so any vector x that has a 0 in the x2 component will map to 0. So xc1 equals, you know, 1, 0. That vector maps to 0, and so this is an eigenvector corresponding to lambda equals 1. Good. But I'm not going to be able to find another eigenvector. I'm not going to be able to find another direction that maps to 0 in this subspace. I'm not going to find any direction that has x, x2 not equal to 0, and x. So the only other direction here that's orthogonal is 0, 1. And that's certainly not an eigenvector of this, because 0, 1 does not map to 0. So this is the only eigenvector for this A minus lambda I. And so what do? We don't have enough eigenvectors. We don't have a complete basis to diagonalize our system, to transform the system into a diagonal form. It's not going to work. And so instead what you do, in this case where you don't have a complete basis and you can't diagonalize your system, this doesn't hold because they don't have distinct eigenvalues, then what you do is next you look for the x's that are in the null space of A minus lambda I squared. Okay, A minus lambda I squared. And so A minus lambda I squared is the subspace of this that maps to 0. So now we're looking for x's that map this to 0, and that's going to give me a second generalized eigenvector. So I should call this xc. Sorry, let's call this xc. Let's call it xc2, in fact. xc2. So this is a second, and we call it generalized, a generalized eigenvector. And so that is essentially kind of an important thing you do when you have repeated eigenvalues. Is first thing you do is you look at A minus lambda I, and if the subspace, if the null space of this matrix, meaning the number of orthogonal x's that map to 0, if the null space of this matrix I'm going to say that again, meaning the number of orthogonal or x's that map to 0, if that null space has the same dimension as the number of times this eigenvalue is repeated, then we don't have to do anything. We just take the two eigenvectors from that two-dimensional null space, and those two eigenvectors will span T, and we can still diagonalize our system, as in this case where it's clearly already diagonal, so that's possible. But if A minus lambda I has a null space that is smaller than the number of repeated eigenvalues, so this null space is one-dimensional, not two-dimensional, so this null space is smaller than the number of repeated eigenvalues, then I'm not going to have enough eigenvectors. I won't be able to perfectly diagonalize my system, and I'm going to have to start looking at generalized eigenvectors down here. Okay, generalized eigenvectors that are going to map to 0. And the generalized eigenvector here is going to be, I mean, in this case, this is kind of trivial because A minus lambda I squared, if I multiply this by itself, again, it just becomes the 0 matrix. So this literally becomes, 0, 0, 0, 0. And so that, again, now has a two-dimensional null space, and so there is a direction perpendicular to C1, another direction that I will need to span Rn, and so I can just pick that to be 0, 1, if I like. Or I can pick it to be 1, 1, if I like. It's a two-dimensional null space down here. So good. Now, I'll give you some other examples of, I'm just going to choose the one that's perpendicular to my C1. Okay, this is going to be, this is C2 equals this. Good, but in this case, I'm never going to be able to perfectly diagonalize this matrix. There is no T that is going to perfectly diagonalize this matrix to have zeros everywhere else except on the diagonal. I'm never going to be able to get rid of this upper 1 here. Okay? And in the previous lecture, I showed you that the solution of this, e to the matrix AT, is equal to e to the t on the diagonal like we expect, 0, and then a t e to the t on this upper diagonal. And this is a consequence of the fact that I can't remove that 1 there. So I get these secular terms that give me, kind of this transient rise before decay type behavior. In this case, it's unstable, so it's just going to be unstable. But if this was minus t's, if this was -1, -1, my behavior would look like this. Okay, good. What else do I want to tell you? So this is more or less just showing you what to do when you have repeated eigenvalues in a problem. You can either have the easy case where the repeated eigenvalues still have two distinct eigenvectors in the subspace of A minus lambda I and the null space of A minus lambda I, in which case no problem, I can still diagonalize that case. So this is not an only if. Definitely if my eigenvalues are real and distinct, then I definitely can diagonalize my system. There will be some cases where my eigenvalues are not distinct, like this one, where I can still diagonalize it. It's still diagonal. Those cases are where my null space of A minus lambda I has the same dimension as the multiplicity of my eigenvalues. This has a null space of dimension 2. This has multiplicity of the eigenvalues 2, so I can still diagonalize this system. But then there is the other case where the kind of rank of the dimension of my null space of A minus lambda I is only one-dimensional, but I have two repeated eigenvalues. I'm never going to be able to perfectly diagonalize this system. I'm always going to have this upper 1, this secular system here. That's an interesting outfall. So now I'm going to revisit this kind of generic picture here. If I had an n-dimensional matrix, what would happen? What are some of the things I can have in my, once I apply these eigenvalue, eigenvector coordinate transformations? So if I had, so what are the cases? What are the just generic behaviors I can get in a linear system with n dimensions? So again, I can get a perfectly diagonal system if I have real distinct eigenvalues, or if I have repeated eigenvalues that are real, but the multiplicity of those eigenvalues is the same as the null space dimension of A minus lambda I, then I can still get this kind of diagonal system here. So that's one case. Another case that we've just seen is that I might have, so this is kind of the case one, kind of the easiest case. Other things I could get is if I have, we're always going to assume that A is real valued. So let's always assume that A has real values. Because this comes from F equals ma, from a physical system. X is real, A is real, time is real, everything is real, at least to us humans. But even for real valued A, I can still have complex valued eigenvalues. So that's case 2. So case 2 would be, I can still have complex eigenvalues. But let's say any complex eigenvalues, any complex eigs lambda, must come in complex conjugate pairs. In complex conjugate pairs if A is real valued. And what that means is that, if I have lambda equals A plus IB, if I have lambda 1 equals A plus IB, then I need a lambda 2 that's equal to A minus IB. That's the only way I can have a complex eigenvalue of a real valued matrix, is if it has a complex conjugate pair. So we've seen this before. In our rotation matrix from F equals ma of the mass on a spring, we essentially had a matrix 0, 1, minus 1, 0. And that real value matrix did have complex eigenvalues, but they came in pairs plus or minus I. Okay? They came in complex conjugate pairs. And in that case, let's say I shouldn't have done A plus IB, but I'm gonna stick with it. In that case, T inverse AT is again, it's not going to be perfectly diagonal, but it is going to equal a block that looks nice. This A, B minus B, A, I bet is what that is going to be based on this. So if I have these complex conjugate pair eigenvalues, then instead of diagonalizing my A matrix, I can write it in a form that has this structure here. And these are going to have those eigenvalues that I wrote down. Good, and the exponential of this, e to the AT, is going to equal something like, cosine, this is going to equal cosine BT sine BT minus sine BT cosine BT. All of that times, do I have a little teeny room over here, times e to the AT. Okay, so it's going to have a real valued e to the AT part, and then this rotation matrix for this imaginary part, plus or minus IB. Okay, so that's one thing you can have. Another thing you can have, case 3, is what I showed you here. Case 3 is where you have repeated eigenvalues, repeated lambda, and a repeated lambda and a not enough null space and not enough null space directions in A minus lambda I. And in that case, you're going to get, T inverse AT equals lambda 1, 0. That's going to be the kind of canonical thing that you're going to get when you do this eigenvector transformation. And these are all called Jordan forms, Jordan blocks. This is the Jordan form. I'll write this down. Jordan was a mathematician. Jordan, not Air Jordans, Michael Jordan, any of the Michael Jordans for that matter. This is a different Jordan, and these are called Jordan canonical forms. This is the Jordan canonical form for a pair of complex conjugate eigenvalues. This is the Jordan canonical form for a set of repeated eigenvalues where A minus lambda I has less null space than the multiplicity of these eigenvalues. This is the Jordan canonical form for a set of distinct real eigenvalues. And so if you have a bigger matrix, like I have a 10 by 10 matrix, it's going to be built up. It's going to be a diagonal matrix built up out of these Jordan blocks. So if I have like 8 distinct real eigenvalues and a pair of complex conjugate eigenvalues, I'm going to get something that looks like this for the upper 8, and then a little Jordan block of my complex eigenvalues on the last 2 entries. And so you can build up this kind of block diagonal matrix for T inverse AT in general out of these Jordan block pieces. I'm going to erase this, and I'm going to say that again, and I'm going to give you a last example of this, but for a 3 by 3 system, and then I'll be done. Okay, before I show you how to build up a big n by n matrix out of these Jordan blocks, maybe I'll just show you the kind of 3 by 3 version of this degenerate repeated eigenvalue case. So there's kind of there's 3 versions of this. So I could have a repeated eigenvalue lambda, 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 a thrice repeated eigenvalue. But I could have a Jordan block that looks like this, that is actually still honest to goodness diagonal. This would be the case if the rank of A minus lambda I equals 0, meaning the null space is 3-dimensional. The null space is basically if this was like a big 0 matrix, and so its null space is 3-dimensional, then I can find 3 clean, unique eigenvectors to span the space, and I can actually diagonalize it. So we saw this already in the 2-dimensional case. Okay. Another way that this can slice is I could have a Jordan form that looks like, again, repeated eigenvalues lambda, 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 zeros below. And then I get a single 1 up here and then zeros everywhere else. This is what's going to happen if rank of A minus lambda I is 1, meaning that this A minus lambda I has a 2-dimensional null space, so I can find 2 distinct eigenvectors but not a third one. Then I'm still going to have the secular term here. And then the last case, I'll go back to orange. The last case would be if I have lambda, 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 0, 0, 0, 1, 1, 0. This would be the case if rank of A minus lambda I equals 2, meaning I only have a single null space direction of A minus lambda I, so I can only pull out 1 clean eigenvector, and then I need to find 2 generalized eigenvectors. So here I don't need any generalized eigenvectors because my null space is 3-dimensional, so I get 3 orthogonal eigenvectors, and I can diagonalize my system. Here, if rank A minus lambda I is 1, so my null space is 2-dimensional, then I can find 2 good eigenvectors directly from this, and I only need 1 generalized eigenvector. I would need to look at A minus lambda I squared for my generalized eigenvector, for a single generalized eigenvector here. But down here, in the case that my null space of this is only 1-dimensional, I need 2 more generalized eigenvectors. So I'm going to have to look at A minus lambda I squared and presumably A minus lambda I cubed to get my 2 generalized eigenvectors out of this. So these are the kinds of Jordan blocks that you can get for a system with 3 repeated eigenvalues. So there's 3 different types of systems that have 3 repeated eigenvalues. These are the 3 types based on the rank of that A minus lambda I, that null space where we search for our eigenvectors to diagonalize our system. Good. What else do I want to tell you? Yeah, the other thing is that for this case here, if I have this 2-dimensional null space, then when I take my matrix solution, e to the AT, I'm going to have terms that actually look like t squared e to the lambda t's. I'm going to get even worse secular terms. So this guy is going to give me terms like t e to the lambda t, but these guys are going to give me t squared e to the lambda t's. And if I had 4 repeated eigenvalues, in the worst case scenario where I had only 1 null space direction, I would get t cubed e to the lambda t secular terms. So there's all kinds of weird stuff that you can have here. Okay, last thing I'm just going to show you. Now, if I have a generic n by n A matrix, okay, so now I'm just going to draw a little line here. So now let's say I have an n by n A matrix. And let's say I have the following eigenvalues. I'm just going to write down some eigenvalues, and then I'm going to draw you my Jordan form for that set of eigenvalues. So let's say that I have distinct real lambda 1, lambda, not 2, sorry, lambda 1, lambda 2, lambda 3, to lambda m. Okay, I've got m distinct eigenvalues. And then also, let's say I have a complex conjugate pair, let's call this lambda plus or minus I omega. Okay, that's a complex conjugate pair. And then let's say I have a repeated pair, and let's give it a different name. Let's call it, mu times 2. I've got 2 mu's, but A minus mu I has a 2D null space. And then finally, let's say I have a repeated pair, instead of mu, let's call it gamma times 2, but A minus gamma I has a one-dimensional null space. Then by finding all of the eigenvectors corresponding to all of these eigenvalues, I can transform my system with T inverse AT into what is called the Jordan canonical form. So the Jordan canonical form that I would get by taking T inverse AT. It's not going to be strictly diagonal, but it's going to be as close to diagonal as you can get for this system. And so that Jordan form, it's going to have a big block that is diagonal. So it's going to be this huge matrix, and it's going to have, lambda 1, lambda 2, to lambda m, zeros here. So this is a block matrix that's diagonal. And then I'm going to have another Jordan block below it for this complex pair. So I'm going to have this little block here, which is, I believe, lambda omega minus omega lambda, this little Jordan block there. And then I'm going to have another Jordan block for my repeated eigenvalues. But because A minus mu I has a two-dimensional null space, I can diagonalize this one. So I'm going to have a little mu 0, 0, mu block. It'll actually be diagonal. And then my final block for these eigenvalues, the Jordan block for this, because A minus gamma I only has a one-dimensional null space, it's going to look like this. And that Jordan block is going to be gamma 1, 0, gamma. And everywhere else is going to be zeros. So this is as close to diagonal as possible, but it's block diagonal in terms of these Jordan blocks. So my real and distinct eigenvalues actually form a diagonal Jordan block. My complex conjugate pair form a kind of skew symmetric block. My repeated pairs that have a big null space are again diagonalizable, and my repeated pairs that have a rank deficient null space have this extra secular term here. And so every single system that is n-dimensional, every single real valued A matrix you could possibly name, you can find its eigenvalues, you can look at the ranks of the null spaces, and you can write through an eigenvector change of coordinates that system into this Jordan canonical form. This is kind of like the universal decoder ring for all linear systems, all A. And if a single one of these eigenvalues has positive real part, it's an unstable system. If all of these eigenvalues have negative real part or zero real part, then it's either asymptotically stable or neutrally stable. Okay, really cool stuff you can do. Okay, that was a lot. That was, okay, but this is important. This is one of the coolest things in linear systems, is kind of getting to this Jordan form. This is really an important concept, so I'm glad you got to see it. All right, thank you.